But I was looking over some of the homework and I just noticed question 10 and I thought you probably want some help on it. So this is my version of question 10 from section 16.8 Stokes theorem. And we have a particle that's moving along a line segment. It starts at the origin, it passes through these points and it ends up back there. It's under the influence of a force vector field. And we're going to use Stokes' theorem to find the work done. And the work done is this line integral. The little circle around it, sometimes they put it in, sometimes they don't. That just means it's a closed loop. And if this was a conservative field, which I believe it's not, then the answer would be 0 and it would be done. But since it isn't 0, we're going to take this guy. Stokes' theorem says it's equivalent to this surface integral, which in turn is equivalent to this double integral. So what's the gist of it? Well, the information that they've given is a bit clunky. They've told us what C is by a sequence of points, like it goes from here to here to here to here to here, but it's not very clear exactly what that is. So that's kind of where my first line of thought was going. Here. You may not know it, but these points all lie in the same plane, right? Remember, a plane's a flat piece of paper in 3D space. And if you call that P and call that Q and call that R, you don't need the other things. If you put them all together, you're just going to have to trust me on this. But you get that. 1/5 Y. So what does D look like? Well, if you take all of these points and then just drop them to the floor. Now, if you drop them to the floor, essentially what you do is you make the Z values disappear. And what you'll notice is that the X's go from 0 to 2 and the Y's go from 0 to 4. So basically you've got this plane, this diagonal flat piece of paper with that equation. But the piece of the surface that we're using is a little rectangle. So imagine a rectangle in the floor meeting up with a diagonal plane. So that was definitely not clear. So now we've got this guy and now we've got this guy. And basically the question is pretty much set up. I'll do a little bit more and then I'll leave it. Since we have this guy, we have to find the curl of F. So it's going to be I giant K. This guy with respect to X, this guy with respect to Y, the last one with a Z, put a Z squared, 2xy, and 4y squared. And the curl of F is going to be so many i's, take away so many j's, plus so many k's. Right, if I cover this guy up, going this way, you get 8y, take away nothing. We go the middle one, we get nothing, take away 2z. If we do the last one, we get 2y, take away nothing. And so it looks like we've got an 8y, two negatives make a positive, a 2z, and a 2y. That means we've got a P, we've got a Q, and we've got an I. So this fella here will be from x equals 0 to x equals 2, y equals 0 to y equals 5, because that's essentially the rectangle at the bottom, right? That's what you get if you take the surface and project it downwards. all this stuff, dy dx. And this stuff is him. And remember that if there's any z's left over, they get replaced by 1/5 y. So hopefully that's enough information to let you do 10. And the hardest part is going to be finding this plane, because what you have to do, if you call this P, Q, and R, you're going to have to find P, Q, and PR and then get the normal. And then you're going to pick probably that guy as your X1, your X1, Y1, Z1. In fact, I think wasn't there an earlier question where we had to find the equation of the plane, but it was a triangle, which was a little bit more obvious that it was going to be a plane. This is less obvious, but can you trust me, as a plane? They're just telling you lots more points than a typical would be necessary.
Professor?
Yes.
Could you pick any 3 of those points as PQR?
Yes.
Okay.
I'm just picking the origin because it looks nice. Yeah, less numbers to worry about. More zeros, less mistakes.
Sure thing.
Is that good enough? Or is there something I've been too vague? I got a nod, so. Okay, that's good enough. So let's get started officially on our last section. It's going to take us about 2 days. Definitely 2 days. If we need to, I guess I'll have to go into Friday. I'm hoping not to, because I want to leave Friday as a kind of revision day. So who's our last guy in town? Well, he's called the divergence theorem. Not a surprise why it's called that, because it uses the divergence of a vector field F. And what the divergence theorem allows to do is to calculate this guy. Have you noticed that all of these theorems, the last 3 sections, have all been about finding line or surface integrals and turning them into something else so that you can do it? So this one says, oh, and by the way, there's only one version of this. You only go this way. So you'll be asked to find a surface integral of a vector field dot ds. And you get it by turning it into, guess what, a triple integral over some solid region E of the divergence of F dV. Now, E is a simple closed region. That's them just covering themselves. It's not like 2 spheres separated in space. It's not like some kind of Klein bottle. Go and look it up. A Klein bottle is a fascinating object. It's an object with only one surface, and its inside is its outside. It's like a Mobius strip in 3D. Weird thing. You do not want to make that your region E. Not that you'll ever will be asked to. So the divergence theorem says that essentially, if you want to find this double integral over surface S, you find the solid region that the surface S is enclosing. So keep in mind, I'll try and draw it. Can you think of this as like the outside surface of an asteroid? This is S, right? The surface of this. Then isn't V the solid? If you have a closed surface, right? That's a surface that wraps itself both sides up and down, left and right, right? So it completely encloses it. So if you poked a hole in it, you could put in water and it wouldn't pop out somewhere, right? A closed surface like that. Would you agree that every closed surface generates a solid? Would that make sense? If you had a surface that was closed, right, enclosed completely, wouldn't it generate a solid, right? So that's what this E is. It's a solid that is enclosed by a surface. And what we then do is we find the divergence of this and we do a dV. Now, since it's a 3D, there are 3 versions of 3D integrals. We're going to look at today the X, Y, Z ones. Right, that's where you describe E in terms of values for X, Y, and Z, and you do a dy, dx, dz, whatever combination you feel like. And tomorrow we'll look at Sometimes the triple integral is easier to do if you think of it as rectangular. You remember rectangular is it's a bit like the polar in 3D, right? X is r cos theta, y is r sin theta, and z is just z. You know, remember that one? That's called cylindrical coordinate system. And sometimes you use this really ugly one, but it can be useful. If the region, right, if the solid region is anything to do with a sphere, you're going to go spherical. If the region is more to do with cylinders, right, some kind of cylinder in a dimension, right, maybe with funny angles at the end, right, so it's not just a tin can, it's kind of tin can with cuts at the end, you're probably going to go rectangular. And if the region is just some kind of nondescript region with no particular structure to it, you're probably going to do X, Y, Z. So let's jump right in. Oh, anything about what I've said that you would like me to say in a different way or just say again? Are we good? Right. So there is no way in the world I'm going to make questions up. If you make random questions up, you never get a good triple integral, right? You don't. You just get some horrible thing that takes, 50 minutes to do. So I've been doing this for a while. I'm just using homework questions because I know they're going to come out good. So in this one, we're being asked to find, as every question is going to be, that surface integral. And we are told that our vector function f is x, y, e to the z, x, y squared z cubed, and negative y e to the z. And the surface is a box. And the surface is a box bounded by the coordinate planes, and x equals 7, y equals 2, and z equals 1. They have essentially told me who E is. So since x is 7, I get that. Since y is 2, I get that. And since z is 1, I get that. And the reason I know it starts at 0 is I was talking about the coordinate planes. You know, the coordinate planes are the XY plane and so on. So if you imagine, they could have said, actually, I wish they had. They could have just said first octant and it would have probably been easier to understand the region. So this one here is very simple. At least, would you agree that the E is known? Because we need to know that. Based on the fact that these are nice numbers, would you agree that this is going to be a dx, dy, dz situation probably? Unless I get really surprised. And now we need to find div of v. So the divergence of f is partial derivative with respect to x, partial derivative with respect to y, and the partial derivative with respect to z. Well, if you differentiate this guy, call him P, Q, and R, right? So if you take P and you differentiate with X, you get Y e to the Z. If you take the middle one and you do it with Y, you get 2x, y, Z cubed. And if you do that guy with respect to Z, you get this fella, which means that since the first and last guys cancel each other out, we get that. We're pretty much done. This surface integral is the same thing as this triple integral. Let's see what we get. For no particular reason, the x goes from 0 to 7, the y goes from 0 to 2, Z goes from 0 to 1 of 2xy, do a Z, do a Y, do an X. And it's been a long time since this has happened.
You forgot your Z cubed at the end of 2xy.
Thank you. Right. I'm so excited to say this. We have finally got a variable separable. How long has that happened? So I can just do from 0 to 7 of the 2x. I can do the 0 to the 2 of a y. And now that you've told me, because I forgot about it, I can do the z cubed. Okay, that's x squared, so that guy's going to get me 49. That's going to give me a half y squared. That's going to give me a half of 2 squared. That's going to get me 2. And that's going to get me a quarter of z to the 4, so that's going to get me a quarter. So I'm going to be left with 49 halves. That is pretty smooth, wasn't it? Considering some of the convoluted stuff that we've done, this one at least is one of the first ones, so it should be easy. It's still pretty. If we go back to the original question, if this is the vector field and you wanted to do this surface integral, I know that the region E is useful, but it wouldn't be if I wasn't using divergence theorem, right? This thing here, right, would be ridiculous because it would actually be a 3D box, which means it has 6 different sides to it, which means it would actually be 6 different surfaces. So you would have to break this shape into S1 the top, S2 the bottom, S3 the left-hand side, S4 the right-hand side, S5 the front, and S6 the back. You would have to do 6 separate surface integrals to do this fill. And that's only the beginning of it. If you wanted to do a surface integral the old-fashioned way, you know, converting it, say, into a line integral 6 times, oh God, that would drive you to drink. Okay. Well, that was a nice start. Let's see where we can go next. So, okay, don't really think I need to do that one. Okay, this is a version of question 3. For completeness sake, I'm just going to put this down because this is what you've been asked in every question, but for completeness sake, I'll put it in. So we're going to find that. We're given a vector field. That looks good. Now the S fella, it's described as the surface, right? So the surface is described in terms of bounded by x equals 0, y equals 0, z equals 0, and a plane called x plus 2y plus z equals 2. We are going to have to work on this because we have to figure out what E, I should say, what E, the solid, looks like. I'm going to try and draw this thing. And not to scale. Since I know it's bounded by x, y, and z, it's basically in the first octant. If you make these two 0, you get an x value of 2 you get a y value of 1, and you get a z value of 2. So the shape that we get is, I don't know if you've ever played one of those games. Do you know the funny little dice that looks like that? It's called the tetrahedron. That's what the solid looks like. Can you visualize that? Right. So I got to figure out how on earth to convert this information into the bounds of a triple integral. Typically what I would do is I would project this guy onto the floor. Now, if you project it onto the floor, you have to change your orientation a little bit. But basically, x is 2, y is 1, and it's down here. And this fella here is the floor, right? So what will I be looking at is, if you rearrange this fella here, you get z equals 2, take away x, take away 2y. And so the z range is going to be from 0 to 2, take away x, take away 2y. Are you happy about how I got the z value? It's basically from the floor to the surface. Now this region here, the floor, is going to then give me the ranges of the x's and the y's. So the way I see it is that x goes from 0 to 2. And if you find the equation of this line, it's 1 take away a half x, and that gives me the range of y's. Are you happy with the limits for x, y, and z of this shape? I got the z's from here, right? Z equals 0, and then rearrange this guy. That was the z's. This triangle, which is basically the projection onto the floor, gave me the x's and y's. And to describe this triangle, I needed to do x from 0 to 2 and y equals 0 to the equation of this line, which is that guy. Now, that's pretty much the hard stuff over. I think finding the divergence is typically just plug and jug, so let's do that. The divergence of f is going to be the 3 partial derivatives added together. And if you take this guy, I'm just calling them P, Q, and R, that way I can say who they are. If you take the first guy, P, if you do him with the respect to x, you get that. If you take the middle guy with respect to y, you get that. And if you take the last guy with respect to z, you get that. And
isn't
that,
the middle one xy squared? So shouldn't it be 2xy?
oh, there's, thank you. I didn't see my little 2, but you're right. 4, 6, 8. You are so good at keeping me in track. Actually, it's nicer, isn't it, because of that? So the guy that we're being asked to get, which is this surface integral, which is typically very difficult to do, becomes this triple integral. And I'm going to do x equals 0 to x equals 2, y equals 0 to y equals 1 minus a half x, and z equals 0 to z equals 2, take away x, take away 2y, and the div is 8xy, z followed by y, finally x. And that guy is going to be the guy that gets us our answer. Are you comfortable about why I did these in the order that they are written? Because any other order would be wrong. Don't you typically do the one with most variables first, the one with fewer variables next, and then the one that's got the numbers? Because the one at the end has to have numbers, or you're not getting an answer, right? It's just not going to work. You're going to get variables. And that's the one that works. Unfortunately, because these limits of integration do not have numbers in them, this is not variable separable, right? We just have to do it, that guy first, that guy second, right? And then finish off. So I'm just going to dot that, right? You can finish that off yourself. Any questions about that one? You feel good? Me personally, I think figuring out what this looks like in 3D and then figuring out how that transfers into these limits is the hard part, right? Being able to figure out how you can describe the 3D solid in terms of restrictions on X, Y, and Z. I don't think this bit was actually that bad. This bit's pretty mundane. Ooh, do I want to do that one? I don't know. What's interesting about it? Ignore me, I'm just talking to myself. I'm looking at 4 and I'm wondering what's interesting about it. I'll show you 4. I think it's better to do that. Okay, this is the one that my brain was having second thoughts on. Whether I need to do it or not, essentially. Or whether it's obvious what's going on. So in question 4, here is your just, don't worry about that. That's as ugly as it's going to be. That's not an issue. It's the surface S. It's described by this guy, and this guy. Now, when you're describing the triple integral, would you agree that you've got the range of x's and the range of y's for free? Agreed? So I guess the question is, what is the range of z's?
Zero to that function.
Right? So that's going to be one of the limits of z, doesn't it? What's the other range?
It says it lies above the xy plane, so the lower limit would be 0, right?
Yes. You know, they could have just said from z equals 0 to the surface. It just made their life easy. Now that I've said that, would you agree this question is pretty much good to go? Right? You would do an x equals -1 to 1. Then next to that, you do a y equals -1 to 1. And then the third position, which is the first thing you're going to do, you would do a z equals 0 to 2 take away x to the 4 take away y to the 4. That is a horrible function up there. But I've got a feeling that when you do the divergence of it, a lot of it just disappears on you and you don't actually get anything that bad. Do you want me to do 4, or do you think it looks good enough for you just to do your own version?
I think it's good.
Okay. If I have anybody who wants to, you can just stick your thumb up if you want to see it, if you don't feel comfortable about talking. No one seems...
Would we be using spherical coordinates for this?
Would you?
Looking at that z, that 2 minus x to the 4th minus y to the 4th.
If it was 2 minus x squared minus y squared, I'd probably be more inclined. But the fact that the x's are numbers and the y's are numbers doesn't really lend itself to spherical.
There's no theta or phi.
Yeah. And there's no... The surface is not a sphere or a bit of a sphere, right? So if the solid region is a sphere, or the surface is the outside of a sphere, which is going to be the same equivalence, then I would think about spherical. It's just going to be powers of x, you know, just x to the 4s and ugly stuff. I'm hoping that at least one of these horrible things like the tan disappears Actually, it does. Yeah, I think the only thing you get left with is the square root of some stuff. So I think it's pretty nice. Okay. Right. Next fella, I am going to do this one. I'm just looking at it. It says, use a computer algebra system to plot a vector field. Well, you can if you want to. It's not going to be something that WebAssign will know if you've done it. But we are going to be looking for our surface integral. And I've forgotten to call this guy the flux. Isn't that what they call this particular kind of surface integral? So we've been finding flux all day today and I haven't even called it that. And the region is a cube in the first octant. So since it's in the first octant, I'll switch over to the whiteboard now. Let's see what we get. So they told me it's x equals pi upon 2, so it's in the first octant, that's the range of x's. This is going to be the range of y's and z's because it's in the first octant. And these are also going to be pi upon 2, and this is going to be pi upon 2. So yeah, you're right, that's a cube in 3D space. I could even kind of sort of draw it. Yay, cube. Right? That's the solid. That's what E looks like. So what we got to do? Well, this fella is done, right? There's E. All I need to do is find the divergence of F. Well, I guess I should write down who F is before I forget. It's a sine X cos squared Y. A sine cubed cosine 4. And a sine 5. Cosine 6. Okay. Call you P, call you Q, call you R. So we're going to do those 3 partial derivatives added up. I am, be really careful. Watch me. This guy gets me cosine X cos squared Y. This middle one, oh good, gets me big fat 0. This end one gets me 5 sine to the 4z's times a cosine z times a cosine to the 6x. Anything nice about them? Nothing. That's a pity. But I can pull out a cosine x, and that leaves me with a cos squared y. Is there any point in pulling out cosine x? Yeah, not really. I could do it, but it's not going to help. Okay, so our answer to this flux is going to be, is there any order that looks nicer than any other order? Not really. So from x equals 0 to pi upon 2, from y equals 0 to pi upon 2, and from z equals 0 to pi upon 2, cosine x cosine squared y plus 5 cosine z sine to the 4z cosine 6x, and do it in the order z, y, and x. I'm looking for something here to make my life easy. Is there anything floating around here that I can simplify my life with? There is nothing in that that isn't even vaguely nice. Bet you the answer is 0. No, it's not even that. Okay. At least with the X's and the Y's, there isn't really much problem, right? Because they're pretty simple, well, relatively speaking. But when you do, let's just do the Z one to show you what our problem is.
That's
And
just a use of.
say again?
The second one won't be too bad. The second term for Z's at least. It's just a U substitution.
Right, I agree. Just time consuming. Right. Okay, so I'm just figuring out how to do this guy. Okay, that looks messy, but it's actually just a constant. So it's going to be the cosine of X, cos squared Y, Z. It won't be a big deal. It's going to be Z equals 0 to pi upon 2. This fella here, I don't really need to worry about the 5 cos to the thingy because that's really just constants. And just like you said, isn't it basically just that guy? Right, so can you actually see this? Am I on the right screen? Because I'm not even sure where I am now.
You're on the right screen.
I'm on the right screen, okay. So those two terms here, the beginning and the end, they're just numbers, so I'm pulling them out. So I'm really just focusing on this, and quite rightly, if you do a U sub, which is sine Z, you end up with U to the 4. U to the 4 integrates as 1/5 U to the 5, so you end up with 1/5 sine 5th Z. I hope I did that in my head right. I got a nod, so I must have. Right, so I guess I don't need this line, but it's just bugging me, so I'm going to do it. Because they cancel out. It's not the biggest piece of help. I was hoping nicer things would happen, but nevertheless. Okay, if you plug it in here, you're going to get cosine X, cosine squared Y times a pi upon 2. Then you're going to take away basically a 0. And then this fella here, you're going to get cosine 6x. What is the sine of pi upon 2?
1.
1.
Right, so it's basically just going to be 1, which means you're going to take away that guy. So this, take away that, I believe that's what you get left with.
Wait, why does cosine x cosine squared y times pi to the half equal to 0?
That's a good question. It isn't, is it? It's pi upon 2 cosine x cosine squared y. I do not like this question at all. Right, so make it look pretty. Just rewrite it again because it's ugly looking. And then off you go and you do an integration with y and an integration with x. And there is no saving grace with that answer at all. And according to what I have in front of me here, the final answer to this one is 19/64 pi squared. I'm disappointed in your WebAssign. You know, you could have probably made that come out as 0 or some nice integral instead of this very clunky one. I guess you don't always get what you want. Oh, we got time for one last one. The vector field is x squared sine y. This guy is x cosine y, and this guy is xz sine y. And S is described as a fat sphere. Interesting name. Must be an American name. I believe actually the Earth is a fat sphere. It's not a perfect square. You know, the Earth is a little bit squished. No? Well, it is. Anyway, you might spend forever and a day trying to figure out how the heck to do limits to get E. But I'm not going to. And the moral of this story is, it's probably a good idea to find the divergence first, because sometimes you get really lucky. This is P, this is Q, and this is R, right? If you differentiate this with respect to X, you get that. If you differentiate this with respect to Y, you get that. And if you differentiate this with respect, you get that. And if you differentiate this with respect to Z, you get that, which means you get that. Since we are going to do a triple integral over region V of the divergence of V, do I really care what the region is? Because, no, because if this is 0, the answer is 0. So the moral of that story is, which I should have actually noticed and didn't, find the div before you worry about finding the limits of the region E. Because I think there's at least one more, not 100% sure, but I think there's at least one more 0 guy out there. So if you find a 0 guy, can't you just, boom, finished? Because trying to describe that fat sphere could be a big problem. And it wouldn't work in spherical. Spherical only works with x squared plus y squared plus z squares. So if you were thinking maybe that's something like r to the 4 equals 125, it's not. Right. So say hi.